This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
You to look at and be familiar with is L section matching. Right? And using, and specifically, using, distributed. So remember there were two types of L matchings, networks, depending on certain circumstances, you would choose one over the other. Right? So you've got to remember that, which one you would use in order to guarantee a solution. And then what I would say, I'd want you to tell me, well, I need to add this much transmission line, this much shunt, this much shunt, this much length of line in order to match the 50 ohms. And then I might ask a couple of very basic questions like, why would you use this one instead of this one, or whatever, right? So, be pretty basic. But, it's important for you to be aware of this, and this is an important part of the course, right? Being able to know, matching and how to build a matching network. And then the third question is going to relate to power amplifiers, of course, right? So the type of question I will give you is I will give you some, S parameters. So I'll say some amplifier is biased in a particular way, and I'll ask you, something: is it stable? Yes, no. But I'll ask you for a proof also, right? Don't just say yes or no, because otherwise you have 50% chance of getting it right. I want to see some working out. Okay. Depending if it's stable or not, I'll ask for some stability circles. For you to draw the stability circles on the Smith chart. Then I'll ask, for you to design the network which gives you max GT. And, very likely I'll ask you is, something to do with the unilateral approximation. Is it good or is it bad or whatever? What do we do? And then probably draw some gain circles. Because I might say, what input and output do I need? What are the inputs and outputs that I achieve a gain of 10 dB or 15 dB or whatever the number is? So it's pretty simple. I mean, if you know those three things, I would be happy. I'm happy for multiple reasons. I'm happy because you'll do well on the test, but I'll also be happy because you know something about art design, and I've taught you something from this course. Right? You can take away and use, at some later stage in life. Right? I assume this is all being recorded, so therefore I'm just making sure that everyone's has this information. All right. So, just show me you're working out. Do it. Just think about it. Think about, how you would calculate this. And if you're in free space, the relationship between H field and E fields. Wave impedance. Right. Remember what radiation resistance means. If you're given a gain, if you're given a pattern, remember how to calculate the gain. Remember it's just 32,000, or 40,000 on angle 1 multiplied by angle 2. So 32,000 divided by those the square root of the sum of those, or the product of those two angles gives you the gain in absolute value, and then you just 10 or 10 of that if you want it in dB. This one, pretty simple. Just remember that there's two types, and which one would you choose and for why. And this one's, just a simple power amplified zone. And what you're doing is, well, a couple of things. You know how to do, the K delta is the stability, and tell me if it's stable or not. If it's not unconditionally stable, then you can work out the stability circles for me, like the input and output stability circles. And what I'll do is I'll try to make the numbers simple, so therefore you don't have to, they're not too cumbersome for you to work with, right? I'll try to do it as much as I can, so that the numbers, but you need to use a calculator or something also, right? The gain, and then you're using unilateral approximation, and draw some gain circles. Okay. All right. Exciting? All right, good. All right. Yes. Someone said something. Yes. Yeah, but that's the question. It's whenever the lecture is, so it should be 2:15. So it said schedule starts, but they've actually put it here. The person's put the time at 2, but it's whenever the lecture is, so it should co-align with the lecture. But if you show up at 2, if you can show up at 2, it's better. Gives me a little bit less stress also, so I can hand out papers and all that kind of stuff. But anyway, all right. So, but it should be co-aligned with the lecture. All right. Now the other thing is tomorrow I'm going to be away, and Thas Nimalathis is going to give you the lecture on noise. All right, just letting you know. So when you see a different lecturer tomorrow, you know that it's planned and as expected. And Thas will talk a little bit about distortion and noise figure and how to calculate that. Okay. All right, and on that note, let's begin talking about what we've learned about gain circles. Now, what we're going to do is I'm going to try to revise some of the stuff that we talked about. We talked about gain circles, and specifically, what I wanted to talk about was how do we use this and what's our thinking, all right? And so far, what I've done is I've said, oh, these are gain circles. Let's assume it's unilateral and blah blah blah. Then what happens if it's not unilateral and it's stable? And then we did we did unilateral, we did unilateral, not unconditionally stable, then we did conjugate, not unilateral, but conjugate match, and then we did, and we're going to do today, just when it's not unconditionally stable and not unilateral. Right, so you can think of it as having the following situation, right? So you can say, okay, I'm going to design an amplifier, and I'll talk a little bit more about this. And I'm going to do the following. I'm given some S parameters, and what are the conditions that we've looked at? Well, we've looked at, unilateral. And we've got unilateral, stable, unstable, and then we've gone, so you can say unilateral approx valid, I should say. We go stable, unstable, and then we had unilateral approx not valid, and stable, and then we did the conjugate match, conjugate simultaneous match, All right, that's what we were doing last lecture on Friday. And today, what we'll do is it's unstable, and what happens here. Okay. So everyone's familiar with that? Like what we did was, initially I said to you, oh, we're going to assume this great thing called, this property called a system is unilateral if S12 is approximately equal to 0, or we had a formula for an approximation, and then we said, if we make this approximation, then we had, how to do it when it's stable and unstable, right? And in this particular case, we looked at one on S11 being the region that we needed to look at. Here we said if it's not, you can't use this approximation, but it's stable, then you can do a conjugate simultaneous match. And we went through that last week on Friday, and today we'll talk about unstable. All right. Now I can't remember if we finished the design example. Does anyone remember? Did we finish the example of design? Did we do this example? I'm old. No. Okay. All right. So let's do this example, and then what we'll do is we'll start off with looking at what happens when unilateral approximation not valid and it's unstable. Okay. So what we're doing here is we're in this situation. Unilateral approximation not valid and stable. Okay, so what we're given here is a microwave amplifier, or essentially we're given in this particular case we want to design a microwave amplifier, and we're given a field effect transistor. We want it to operate at 6 gigahertz, and we want to determine what the maximum transducer gain is when we have these scattering parameters. And I'm missing a Smith chart. Missing a Smith chart. Okay. All right. So what we did was, so we calculated, so we were given S11. The first thing we want to do is determine if the system is stable. Of course, we do the kappa delta test. And if we do this, in this particular example, what you'll find is kappa is 1.5, delta is less than 1, so the system's unconditionally stable. Now, the next thing we want to do is to check if this transistor can be considered unilateral. Essentially, what we're doing here is validating if we can use the unilateral approximation, right? Which is, can we say, even though in this particular case S12 is small, we can't just look at it and just say S12 is small, in this particular case it's 0.057, and we can neglect it, right? Because what specifically the test is how inaccurate is our gain going to be if we make this approximation? And what we did is, in the last lecture, what we had derived is a formula which tells us our relative error. And what we did was we found the bounds, the upper and lower bound for the ratio of the transducer gain divided by the transducer gain using the unilateral approximation. And the values are bound between these two values, where U is given by essentially this formula, which is a function of S12, S21, S11, S22, and then the differences, essentially the reflection coefficients at the input and the output. Now, if we go through this, what we find is that the error is between 0.9 dB, 0.89, we can, for argument's sake, for this lecture, we can say it's 0.9 dB and 1 dB. So we've got 1 dB error. So the truth is, usually, as engineers, depending on the thing that we're trying to do, that in most cases states that if we got 1 dB error, that's 10%. So really, we shouldn't be neglecting S12. So therefore, we cannot use this unilateral approximation. Okay. So what that means is, if we can't use this unilateral approximation, yes.
That should be no S12 can be, right?
Sorry, which one? What did I say? S12 cannot be neglected. Cannot use unilateral approximation. And gamma S and gamma L optimal are interrelated.
Choose only in this situation is no S12 can be neglected.
No, S12 cannot be neglected. Cannot be. Because what we said was, if we went through here, if you remember in the lecture, when I did the unilateral figure of merit, right? When we did the unilateral figure of merit, this is slide number, is it 16 or 11? I can't even read my writing. 11. Okay. When you do the calculation, we said that you can neglect it if you're about 1/4 of a dB, right? In this particular case, we're about 1 dB, right? So under those circumstances, it's not good to neglect it. That's what I'm saying. Does that make sense? Okay. And essentially, yeah, and what it also says is there's a relationship between the input and the output impedances. All right, and in order to do that, I've given you a set of formulae, if you remember, in order to calculate the optimal reflection source coefficient and load coefficient, and I've written them in terms of these quantities called B1 and C1 and C2 and B2, where B1 and B2 are given by the following formulae, and delta is the S11, S22 minus S12 multiplied by S21. Okay, so I've actually written it here. So when you go through this, you can actually work out what B1, B2, C1 and C2 are, and you can also then determine by substitution what the optimal source reflection coefficient and load reflection coefficient is. And these are the two values. Now, we've also gone through and said we can actually work out the maximum transducer gain, which was K on K squared minus 1. Now, did you, I think somebody was telling me that I've substituted in the wrong values. I can't remember. Was it you that was telling me I made a mistake? This is the one that I've made a mistake in, or in my substitution or my arithmetic? Is that correct? Is this the one that you said that you didn't get this value?
But it's different.
Okay. Anyway, this is the formula for GT max, and GT max is essentially magnitude of S21 on the magnitude of S12 brackets K minus square root of K squared minus 1, right? And if you go through this, you can actually work out what your GT max is, and also you can also work out what your maximum stable gain is, which in this particular case is 15.7 dB. That should have a dB behind it. Okay, so dB, or this is in linear units. Okay, so essentially what this, all I did here was say, well, okay, the unilateral approximation was not valid. It's stable. We have to do a simultaneous conjugate match, and this is what my gamma S and gamma L optimal values are. All right, let's start on this case today. Okay. So today we're looking at the fourth case, and essentially what we've shown, or what you can actually show, is that when S12 cannot be approximated by 0, or you can't use the unilateral approximation, and the system is not unconditionally stable, you can take it as a fact, but what you can actually also prove is that you cannot, under those circumstances, achieve a simultaneous conjugate match, right? So under those circumstances, what we do is we look at, instead of looking at the maximum transducer gain, we look at the operating power gain, okay? And if you remember, if you go through your formulae and you go through this, you can actually work out or remember what your operating power gain is in terms of the input impedance, S21, and the load impedances, right? And likewise, we know what gamma E, the input reflection coefficient, is in terms of the load reflection coefficient. So what we do in order to move this forward, what we do is we define the constant operating gain circles, right? And these constant operating gain circles are essentially, what we do is, like we did in the previous sections, we define this concept called GP, little GP, right? Which is the ratio of the gain that we want to achieve to S21 squared, right? That's its definition, okay? And if you go through this, you can actually show that this quantity on the left is equal to this, and what you're able to do after some algebra is to work out, like we've done in the past, what the centre and the radius of this particular circle is going to be for this particular desired gain, or GP, little GP. All right. Now, GP is a little GP, so that's operating power gain. All right, and then what I've done is I've normalized, all I've done here, if you're just looking at the little, you're asking what that little GP is? Is that what you're asking? Okay, this little GP, I've defined it. This one, this definition is new. Okay, new definition. So don't, new definition. Big GP has been defined, right? That's been defined in the past, right? And if you remember, we had GP. Let me try to grab my notes so you can actually see that I'm not making all this up. So, this is the GP that I'm talking about. So it's the operating power gain, which is the power delivered to the load relative to divided by the power input to the network. Okay, that's the GP I'm talking about. Right, and we've gone through and we've actually derived what that value is actually equal to. But anyway, that's the value that we're talking about today. And that's, again, under these circumstances only. All right. And the reason is because we can't do a simultaneous conjugate match under these circumstances. You can actually prove that you can't do that simultaneous match. So what we're going to do is we're going to say, well, let's now assume that we're going to maximize the available power of the operating power gain. And what we do is we work out the circle, the gain circles for this, And we also say, or we also determine that we know that the optimal value of gamma L equals to when this the radius of this circle equals to 0. And what you can do is you can continue on and actually solve that equation and then show that a solution to this equation occurs when GP, this little GP max, is equal to 1 on the magnitude of S12, S21, magnitude thereof, k minus k squared minus 1, right? And we've defined k squared minus 1. And likewise, remember we had defined little gp as being the ratio of gp on S21, so therefore that allows us to then calculate what gp max is. Okay? Now, rather than worrying too much about the derivation, let's talk about the procedure on calculating or determining the maximum GP gain, or determining the GP gain for an unstable system. And what do we need to do in order to determine that? So the very first thing that you need to do is, once you're given the scattering parameters, what you need to do is to determine the input and the output stability circles. Right? How do we do that? We look at the formulae, we look at what, and we work out the center, we work out the radius. How do we know how to draw it on the Smith chart? This is stability circles, guys. We look on the bottom, right, in order to work out what the radius is. We draw the point at that angle, and then what we do is we draw the center point, and then we work out what the radius is, and we draw the radius around that. What do we have to worry about? If we're, sorry? Yes. Why? Right. Exactly. Exactly. Yes. Right? Perfect. That's good. All right. Yes. Right. So therefore what we do is we draw the center and the radius, and then we got to work out if it's, which region is stable. Is it inside or outside the stability circle? If it's greater than 1, it's outside the stability circle, and the region of instability is the intersection of the inside the stability circle and this intersection with the Smith chart. All right, perfect. What happens if it's greater than 1? The intersection of you have a circle in the Smith chart is the stable region. Yeah, good. All right, excellent. All right, so first step, draw the stability circles, right? Second step, draw the available power gain, the power gain operating circles, right? And we said that GP is, these are the following definitions for GP, and the center and the radius. Okay, and we know, I now confused myself. Where have I put my, yep. All right, so we work out that. We know, we want to work out where GP max is, and GP max is going to be what? Is it going to be a circle, a point? A point, all right. And looking at this, when do you expect it to be a point? When k equals? All right, let's, all right. I'll let you go through that. All right, so I mean, this is a little bit of an exercise for you. All right, so therefore, once you've done this and you've drawn for a particular gain, and because you can actually work out what your GP max is, right? And you work out GP max when k equals to 1.
and that's where GP max occurs. Now, the next step here, which is going to be a little bit different to what you're usually used to, is if you're given, or if you're asked to determine or select a particular GP, what you do is you have to select a gamma load, right? Where would you select gamma load? And remember, what we've done here is we've now got these gain circles, and these gain circles, what we're looking at, right? And we choose the gain circle. For example, we might choose 10 dB or whatever, but it has to be less than GP max. That's the point, right? So that's the reason why you've got to also calculate GP max, because you might say GP max might be 12 dB, and I might ask you to do 15 dB, and you can say to me, Stan, that ain't never going to happen, right? So you draw the circles, you then choose a reflection coefficient, and you want to choose that reflection coefficient so that it's in the stable region, right? You can choose it. So you choose it on that particular gain circle, right? And you can choose it anywhere you want on that gain circle in order to achieve that gain. But generally what we do choose is, in many cases we try to choose it so that it's closest to the origin, or the one point, or the perfect match point, in order to have the smallest standing wave ratio at the input. Now, you can also choose it so that it has the maximum real parts of it, where it's the most stable. It depends on what you're trying to do, right? So last time we said we chose it because we wanted maximum stability, so therefore we chose it so that it had the maximum real part. Or you can actually choose it so that it's in a stable region, but also closest to the origin, so therefore I've got the maximum standing wave ratio at the inputs. But that may also present some challenges, and we'll talk about that in our example. Okay. So what you do is you determine gamma L. Once you've chosen gamma L is for you to choose, right? In this particular case, you can actually work out your input impedance, or input reflection coefficient, I should say. And likewise, in order to get maximum power transfer, you would choose the source reflection coefficient to be the conjugate match to the input reflection coefficient, right? That's in order to get maximum power transfer. And of course, maximum gain, right? But there's a problem here. There's potentially a problem. What do you need to check? Well, you need to check that the source impedance that you're choosing is actually inside, stability circle, so that it's stable. It might happen, right? In real life, it wouldn't be in an exam question or how do you call it, a test question, but in real life, it might happen that you've chosen gamma L that gives you the best load standing wave ratio, but it gives you, it's unstable, right? Under those circumstances, what you would do is you'd go back and choose a different gamma L, right? And you choose it so that it gave you some desirable property, right? Now, here you can do another thing, which is you're also at liberty to choose some other gamma S, right? You can actually say, I'm going to choose gamma S to be, the conjugate, the complex conjugate of the source impedance to be, the source reflection coefficient to be the complex conjugate of the input reflection coefficient. But that's the one that gives you the maximum gain. You can also, instead of saying, well, I'm not going to, I really like what's happening at my load, right? I've set it up so that I've got a very good voltage standing wave ratio. You know what? I'm prepared to tolerate even a little bit more loss in order to have, for the system to be stable. So therefore what I'm going to do is I'm going to ignore this gamma in, or this complex conjugate matching in order to achieve maximum gain, and I'm going to choose it some other way. That's your prerogative. You can actually do that, right? You're not constrained to do that. You can actually choose it so that, hey, it still gives me something desirable. Okay. And then what you do is you say, well, all right, we're all good, and now we're going to look at as part of the exam or test questions, you're all done, you finish, but generally what you would do is you would look at the voltage standing wave ratio in order to ensure that both your input and output systems were not only stable but also had desirable voltage standing wave ratios. What does voltage standing wave ratio mean? What's the voltage standing wave ratio? Sorry, I'm not... Yeah. You remember that? Okay. So what we did is, remember we went through and we said, this is our voltage standing wave ratio. It's essentially the maximum voltage to the minimum voltage that we get on a transmission line. Right. Likewise, what it's saying is if you've got an amplifier and you've got to build a particular matching network to it, the voltage, the minimum voltage and the maximum voltage at the input varies from these two values, right? So therefore, the closer to 1 it is, it means the smaller the maximum to minimum voltage. The larger it is, the larger the difference, right? How did we calculate that on the Smith chart? Who can remember? We did something on the Smith chart. Remember we were looking at transmission lines, and let me grab a clean Smith chart, one that I haven't scribbled on. What did we do? If we had, suppose I gave you a point there. How would you work out the standing wave ratio? Radiant. Was it radiant? Okay, remember what we did was we drew a line to this point, and then I had my dangerous instrument that I've lost. And what I would do is draw essentially the circle. And then what I said was just work out this distance and read it off here. And that would give you, I mean, you can actually just read it off directly, right? But, and you can say, this is my standing wave ratio. So if it was 0.5, it would be 2.25, right? Sorry, I misunderstood. Okay. You said radians, didn't you? Radius. Okay. Radians is pi, right? Like angle. So I thought you were saying to me, measure this angle rather than radius. Yes, I apologize. Radius is correct. Radians is not correct. Okay, good. All right, now let's do an example. All right, so since we're remembering everything, okay. Who wants to be brave enough and go through the process for me? So we've got a field effect transistor, and let's remove this. And I've said it's got these scattering parameters. So the first thing is definition. What's the maximum stable gain? All right, you can look it up. You've got the notes anyway. It's not as if I hadn't put the notes up, then it could be different. So maximum stable gain is essentially the ratio of S21 to S12. And in this particular case, it's 31.25 or 14.9 dB. What does that mean? It's the maximum gain that we can achieve, and the system's going to be stable. All right. So if I said to you, draw me the gain circles for 17 dB, what would you say to me? Okay, good. All right. I then say to you, design me this amplifier such that it has a total gain of 10 dB. All right, what do I do? We have to calculate small g. Okay, what's small g? It's GP on S21 squared. All right? Suppose this value was 3 dB, right? What value would I put here? Yes. Yes. Okay. So everyone realizes what I've said? What your colleague has just pointed out? You don't put the dB value there. You calculate, you turn it into linear, and then you put that value. Don't put dB there. It's a common mistake. Right? So if this was 0 dB, right, as an example, don't put 0 there. Put 1. Okay? All right. It's a common mistake. Everything is done in linear scale, right? Don't be confused and forget and leave it in dB. Okay. Now you can do a little bit of arithmetic, and you can work out the center, CP, and RP. And what else do we need to do? So we've worked out, if we want to achieve 10 dB gain, we know where that point is. The center of that circle is going to be at CP, and the radius is going to be at RP. All right, and I believe I've actually calculated it somewhere. What am I doing today? Oh, yeah. All right, and you can work out what CP and RP is, right, in order to achieve this. Now, is this system, what do we have to also do? Usually we have to draw the stability circles, but if it's unconditionally stable, let's say we did the what test would we use in order to work out if the system's unconditionally stable? Kappa delta, right? We will calculate kappa and delta. We're going to make sure that this is greater than 1, this is less than 1, right? Stability test. If it's unconditionally stable, it would be kappa would be greater than 1, delta would be less than 1. Now, in this particular case, because I'm telling you to draw the stability circles, okay, if it was unconditionally stable, let me ask the following. If it was unconditionally stable, where are the regions of instability on the Smith chart? Sorry? Yeah, you go. He always asks answers. They can be, yeah. So there will be no, so therefore, if it's unconditionally stable, all the points on the Smith chart are stable. So you don't have to do anything if it's unconditionally stable. If it's not unconditionally stable, what do you have to do to work out the regions? Okay, perfect. You draw the input and output stability circles. Perfect. Okay, and in this particular case, what we need to do is start off by drawing the load stability circles, right? So therefore, we draw CL and RL, right? We work out the center and the radius. Okay. Where's the stable? Is the stable region going to be inside or outside the stability circle? So the stable region's outside the stable circle. That's right, stability circle, because? Yeah, Yeah, perfect. Or S22 in this particular case, because we're looking at the low. Yes, okay. Alrighty, so now let's draw both the stability circle and the gain circle. Now, the truth is, I've tried to draw this by hand because I lost my compass. It looks really distorted, right? And actually, if you do it properly, it doesn't go all the way through to 1, 0. It hits somewhere there, right? And I apologize, I just didn't have I tried to do it with a ruler and whatever, and it became a mess. So I apologize for that. So what we do is we draw the point CP, and how do we draw the point CP? We said, first of all, we work out the angle. We said it's 97.2. We look at, for the reflection coefficient, we find the angle 97.2. We draw a line there that tells us that the center CP is going to lie on the line joining here, the center to this point. And the way that we work out the length along this line is we measure out 0.72 with our compass, 0.72, and then we draw it, right? And then we draw the circle, given the radius. Okay, and also we draw the output stability circle. Okay. Now, what gain should we choose? Gamma L. All right, so what happens is, if it actually went through the origin, what you would do, or the 0.11, you would choose the point, you would choose this point, but it doesn't. It's somewhere around here, right? So what you would do is you choose roughly that point, so therefore it gave you the minimum load voltage standing wave ratio. All right? So you would choose that point. If voltage standing wave ratio was the most important, if you want the maximum stability, you would choose it somewhere here, right? Maximum real part. Okay. Now, once you've got gamma L, you can work out what gamma in is, and you can work out what this value is. Great. And we say for a conjugate match, gamma S is equal to gamma in conjugate. Right? Now, what do we have to do next? Well, we have to draw our input stability circle. Right? I haven't drawn it here, but you would just draw your input stability circle and actually work out if this particular point is stable. What you find is that it is actually stable, so you don't have to worry about it. But what you do find is that when you work out gamma out, right, or that you're at this location, right? If you try to get a conjugate match, that's your output impedance rather than your input impedance. And if you look at that, what happens is it's not desirable, because what it's saying is our voltage standing wave ratio is 25 to 1. Now, for the test, that's fine. For the exam, it'd be fine. But really, what you would say to yourself is, hey, this isn't really desirable, guys. Let's forget about that. Let's choose another point, provided it's not inside, it's outside the input stability circle. And what you would do is you would just find it so that it gave you desirable voltage standing wave ratio. Here I've just said you can do it, you get a value, but the value is not a great value, right? It gives you the maximum, it gives you the 10 dB gain, but the problem is that it's also giving you a terrible voltage standing wave ratio. In a real system, you don't want that. If you're designing a power amplifier, you don't want that, right? That's the point. You don't really want that, because large voltage standing wave ratio, it's sensitive, it's, a whole bunch of issues, right? So what you would do under those circumstances, you would choose a different point as in order to get your source impedance, or choose your source reflection coefficient. You wouldn't choose it as the complex conjugate. And that's it. That's all you need to do. Okay. That's it for today. All right. I'll give you a few minutes to to contemplate. But yeah, like, I mean, I strongly recommend that for, I mean, as you can see, I mean, a lot of you are probably much better at drawing than I am, but I strongly recommend if you've got a compass, get a compass for the test and also for the exam, because usually it's really hard to draw circles. I find that impossible. Then we take it from there. All right. All right, so see you all on Friday. There's a lecture, but I'm not taking it. I've asked somebody else to take it. Not happy, eh? You preferred if I cancelled it. I know, but I think you wouldn't learn about noise figure. You want to learn about noise figure, right? So, who's actually taken, as part of this course, I'm just out of curiosity, you can say, has actually gone out and gotten a transistor and biased it up and actually tried to make it work as an amplifier?
Excuse me, how to calculate the gamma out?
Yeah.
Gamma out, it's
the most stable part.
no. Okay, so you got gamma S, right?
Yeah, we got cameras.
And you got gamma L, right?
Yeah.
So you've chosen gamma S.
And calculate.
Yeah, you've said gamma S. You wanted gamma S to be gamma in conjugate, because that gives you the maximum gain. All right, and then you just put gamma out using this formula, and you're done.
Oh,
Okay.
Fine.
and in this part, we need to first ensure that gamma in is in the stable structure.
Yes.
And then use this one.
Yeah.
But if not, what value of gamma S can you choose?
You can choose what it says. Yeah, and that's what I said. Not random. Choose one that's stable, but it will give you it won't give you the maximum gain.
That is close to the original one.
Usually you try to do that so that where you get minimum standing wave ratio. Right. So there's a lot of flexibility that you've got, but you know they're the kinds of things that how you would draw.
So you calculate this value and then to the Smith chart you see it's in the outside the stability circle, so it's in stability.
No. The output stability circle's there, and then it's fine. So it's there's no.
So this point is outside this circle.
I know, but I've got to draw. No. That's fine. That's the output. I've got to draw the input stability circle.
So
And
the input circle is causes central point is 1.67 and it's 171, so it should be like
yeah. So that's not unstable. So it's okay, but it gets close. That's why you got this terrible voltage standing wave rate. I haven't drawn it.
It maybe look like this part.
I just confused about the point in the last lecture,
Yeah.
and very confused lecture. Why can't
Yeah.
you get here?
I'm going to confirm that, but I think okay. So what you try to do is you know that the optimal source impedance. I've got to confirm, is it conjugate or just one on S11? I've got to confirm it because I think I might have made a mistake.
Yeah, it's because you says.
Yeah. I think yeah.
Yeah, cause when you
Yeah, mistake. I think so, but let me confirm it. I think it's a mistake. Yes.
yeah.
Right. Yeah, I'm gonna start just copying the book. I'm not gonna start writing notes. I'm just gonna say read the book.
So, but I cannot find this content in the microwave engineering this textbook. So you change to another textbook.
It's what I know. That's what I'm doing. This is stuff that I know rather than how do you call it? Than looking at a book, and that's why there's all these mistakes. Because it's just I'm there saying I want you to learn this, but let me see if I can find the book. I think Gonzalez has got it. So, microwave transistor amplifiers. Microwave transistor amplifiers for Gonzalez.
Okay.
Thank you. Okay, just give me a couple of seconds. And I can ask. I mean, I don't want you to pass the back to the office. We can help us. Okay. I don't think so about that.